Before we go further in the subject of classical mechanics, I would like to review certain mathematical quantities which we are going to encounter frequently in this course, and it will help us keep our later discussions uncluttered. Okay, so we record everything here of all those things which we will require, and later we will just make a reference to what we have discussed today. Okay, so that's the plan, and here is our whiteboard. So as you can see, I want to talk about matrices today. Most of the things you will be already familiar with, and maybe something not. But generally I will assume that you already know, and I'll go fast with that. Okay. But if you have not encountered certain things, you will still be able to understand from this discussion. Okay, so what I want to do is a quick recap. So mostly I'll be dealing with square matrices. So if I do not say specifically that I'm talking about a square matrix, you assume that I'm talking about square matrix. So I will be only talking about square matrices in this, and in general they will have a dimension n cross n. So n number of rows and number of columns, that's what a square matrix is. And as you know that to a matrix you can define a transpose. So if you have a matrix M, a square matrix, you can define a transpose M transpose, which you obtain by interchanging the rows and columns. Okay, let's see how you write this down in index notation. So if I want to tell the indices of tell the element of a matrix, so I specify ith row, element at the ith row and the jth column, so that you say mij. So this is the entry mij. Okay, so how this mij is related to the elements of M transpose? It's like this. So let's say you ask M transpose, you take that matrix and ask what is the element in ith row and jth column. Okay, and as I said, it's just the interchange of row and columns of M, so it should be mji. Okay, so this is how you should write this expression. Okay, you always have identity matrix at your disposal. Okay, so identity, and whatever problem you're doing, if it involves matrices, identity is there. And identity is all the elements on the diagonal are 1. If you are off the diagonal, it's 0, which means the components, if I want to write down in components, then you can represent your identity matrix by Kronecker delta ij. Okay, that's good. If you have a symmetric matrix, okay, then it implies that M transpose is same as M. Okay, which means that, so let me do it slightly slowly. I know many students get it wrong when they try. They should not, but they do. Let's do this one. Let's say M transpose equal to M, and I want to write down this expression in component form. So I want to use indices I and j to write this. So what you have to do is, on both the sides, so this is a matrix equation, and let's say I want to know ijth element. So I should take the ijth element on the left hand side, I should take the ijth element on the right hand side, which is what this equation is saying. And this implies, and you have already seen what M transpose ij is, it is here mji. So you get mji equals Mij. That's the condition for a matrix to be symmetric. Okay. Let's look at an anti-symmetric matrix. If you look at an anti-symmetric matrix, so when you transpose, you get a minus sign. Okay, so you should have Mji equals minus Mij. That's good. Now that's easy. Let's go to the next, and you can say this is a theorem, of course, a simple theorem. Given any square matrix M, you can always decompose that matrix into a symmetric and anti-symmetric part. Okay, and in fact you can do more. You can take the symmetric part and further decompose into two parts, one which will be traceless, another which will carry the trace. Okay, so I'll show you a square matrix can be decomposed into a symmetric matrix. I want to, as I said, I can decompose the symmetric part further, so into a symmetric traceless matrix, a matrix that will be proportional to identity, which you will see immediately why. And then an anti-symmetric piece. Anti-symmetric okay, the proof is almost trivial. So let's say you have M, which is n cross n matrix. So I can write down M as M plus M transpose by 2 plus M minus M transpose over 2. Okay, so let's check whether it's fine. It's fine. So M transpose gets cancelled by M transpose here, and you have M by 2, M over 2, and they make M. So this is fine. Okay, this is your symmetric part, and this is your anti-symmetric part. Why is it symmetric? Because if you take a transpose of this entire piece, you will get M transpose plus M, which is same as what you already have here. And if you take the transpose of this piece, you will get M transpose minus M, which is the negative of what you have here, and that's why it is anti-symmetric. Okay, so in the component form, I can write this as Mij equals Mij plus Mji half. Okay, that's the first symmetric piece, and then you have Mij minus Mji over half, over 2. Okay, that's your anti-symmetric piece. And as I said a couple of minutes ago, you always have identity matrix at your disposal. Okay, now identity matrix is a symmetric matrix. So out of this symmetric piece, okay, here I can take out or I can subtract any matrix which is proportional to identity. Okay, and filter that out. And what will be useful is to take out a matrix which is proportional to identity, of course, and the proportionality factor is the trace of M. Okay, so that's what we want to do. So let's have a look at it. So let's say look at this. identity, which is a symmetric piece, I multiplied with trace of M. Okay, now this is what I want to add and subtract in the above expression, but I have to be careful because let's say I multiply with some factor k and I will fix the factor k. That will be easier way of stating all this. So what I'm saying is I will write M. So I add here k times trace of M. Trace of M is some number, it's not a matrix, times identity. Because I've added this, I want to also subtract it so that I don't change the equation, times identity. Okay, that's good. Now let's see what the k is. From here, whatever k you take, it's all fine, but what I want to do is I want to club that term with this. Okay, and what I want to do is that this entire this plus this should be traceless. That's what I want to do, and that will fix the k for me. Okay, otherwise you cannot fix k. This is identically true. So let's see. So what I want to do is I want to take half mij plus mji, the term here and the term here, plus k trace of M into identity. Okay, I want this piece to be traceless. That's what I require. Make this traceless. Okay, so let's see. Let's take the trace of it. So I take the trace of it. What do I get? I get half from here, trace of the matrix, and its maybe and that not the transpose is the same. Okay, but I hope you already know that the trace is written as MII, meaning I am summing over the repeated index here. So what is trace? Trace is the sum of diagonal entries, and if you are summing over all these, that's what you get, the sum over all the diagonal entries. So M11 plus M22 and so forth. So here when I'm taking trace, all I have to do is identify I and j and use the Einstein summation convention. So it becomes half MII, which is the trace, again MII, which is the trace of M, plus k is a constant, trace M is a constant, so there is nothing happening there. And then you have identity matrix, which has 1, 1, 1 n number of times on the diagonal. So if you take a trace, you are adding up all those ones, which gives you n, right? Because I'm saying n cross n matrix. And this we want to be 0. This trace we want to be 0. Now this is trace of M, 2 trace of M, these two together, and there's a half, so which gives you trace of M. There's a trace of M here. So from this equation I can remove the trace of M, and what will be left with is 1 plus k times n equals 0. Okay, right, and which means that your k is minus 1 over n. Good. So here in this place I should replace minus 1 over n, and here again, which will make it plus 1 over n because of the minus already which is present. So yeah, so that's, let me write down again. The result is your M I j can be written as Mij plus Mji half. Okay, that's what you already have. Then minus 1 over n, that's what you found, and then you had the trace term, trace of M, and that then you have the identity, and identity is delta ij. Okay, I'm writing in components. Okay, that identity I should have written delta ij here, but it's okay. So you see a minus 1 by, it was n, minus 1 by n trace m times identity. This identity please write down as delta ij. Okay, here also. Okay, so that is your traceless part, plus 1 by n trace of m delta ij. That is your trace part. So you have filtered out the trace, and then you have the antisymmetric piece, half mij minus mji. Okay, so that's the decomposition which you can always make. Okay, that's good, and I believe you already knew it. Okay. Now we want to talk about the number of independent entries that you have in a symmetric matrix or an anti-symmetric matrix. Okay, that's what we want to do, and I'll count these in two different ways. So first let's look at a symmetric matrix. Okay, so for symmetric matrix, if you have n cross n matrix, the total number of entries that you have in the entire matrix is n cross n. Okay, so total is n square. So to begin with, we have n square elements, but of course not all of them are independent. So let's draw here a symmetry matrix. Let me write down. So you have something here, let's say a 3 cross 3, just for the sake of explanation. Okay, you have some entries at all these places. Okay. Now if this is symmetric, which means apart from the entries on the diagonal, whatever you have above, the same thing you have below. Okay, so this guy is same as that guy, this guy is same as that guy, and so forth. So if I can count how many entries are here, I'll be done. So how do I get this? So in total you have n square. If you count everything here, you have n square. So out of n square, you remove what you have on the diagonal. On the diagonal you have n entries, right? First, second, third, and so forth. So n square n is what you have other than the diagonal entries. Now you divide by 2, you get what you have in the upper triangle, upper half. So you divide by 2, which is same as n into n minus 1 over 2. So these are the total entries in the upper half, upper triangle. Okay, in the upper triangle. That's good. So how many we have in total independent ones? Of course, the ones which you have calculated just now, these ones, and I don't bother about these because they are same. And then of course the n on the diagonal. So I should take these n which are coming from the diagonal ones, and then these coming from here. And how much is that? That is n, you take n outside, 2 plus n minus 1 over 2. This is n, 2 minus 1 is 1, which makes it n plus 1 over 2. So these are the total number of entries which are independent for a symmetric matrix, which is correct. Let's check. Let's say you have a 3 cross 3 matrix. So if you had a 3 cross 3 matrix, you should get 1, 2, 1, 2, 3 and 4, 5, 6. 6. Let's see. If n is 3, this is 4. 3 plus 1, 4. 4 over 2 is 2 and 3 times 2 is 6, which is correct. Okay. Now I want to count it in a slightly different way and arrive at the same answer. Okay. So that was first way of looking at it. Second way, not really different actually. So here I say that I have n square elements or parameters which parameterize a symmetric matrix, and then I say how many conditions are there, how many constraints are there on these parameters, and I will remove out of the total number those constraints and I'll get the number of independent parameters that parameterize a symmetric matrix. Okay, so that's your total number of parameters, not necessarily independent, total number of parameters. Okay, and how many constraints do you have? Let's look at constraints. So the constraint is that Mij is same as Mji. That's what a symmetric matrix is. Now if I equal to j, it says Mii equals Mii. So this is not a constraint. It says whatever you have is whatever you have on the, so it says M11 is M11, M22 is M22, M22. That's saying nothing. That's not putting any constraints. So these don't give any constraints. And only when I is not equal to j you are going to get constraints. Okay, so when I is not equal to j, it says Mij equals Mji, which is, for example, M12 is M21. So that's a constraint. And how many of such constraints you have? Now you can see that I can take any of the n values, then j can take any of the remaining n minus 1 values. Okay, I don't take again n because one of them is here, right, when they become equal. So n can take any of the n minus 1 values, which is good. So these are the number of constraints, but we are still overcounting because M12 here, let's say it is 1 and 2, and M21, these are same relations, right? So it says M12 is M21, and again you get M21 is M12. So you're counting twice, so you divide by 2. So these are the total number of independent constraints. Yes, total number of independent constraints. So here you have the total number of constraints is n into n minus 1 over 2. Okay, so how do you get the total number of parameters, independent parameters? You get by taking the total number of parameters that you have minus the total number of constraint equations that you have, which is n into n minus 1 over 2. Let's see what that is. This is n. I have taken out common, and you have n minus n plus n minus n plus, sorry, that's what am I doing? Sorry. Okay, so I have taken n outside, so you have an n. This n is gone, so only minus. You have n minus 1 by 2. What am I doing? Yeah, sorry. N minus 1 by 2. That's correct. So you have n. 2n minus n gives you n. That makes a plus 1. And you have a half here, which is, let's see what you got earlier, n into n plus 1 by 2, which is same as before, right? So that's how you count for a symmetric matrix, that it has these many independent parameters. And for a anti-symmetric matrix, it is the same calculation, except for the fact that on the diagonal you have nothing. Okay, the diagonal entries are 0, so you remove those n entries. So let's see. So for an anti-symmetric matrix, what we can do is we can take the previous result, which was n into n plus 1 over 2. Okay, n into n plus 1 over 2. But now I have nothing on the diagonal. They are all 0, so there is nothing to choose. They are not in. You cannot make a choice of what should be on the first entry, what should be the second entry on the diagonal. So you remove them, okay, because that's in here. So what do you get? You take n outside, you have n plus 1 over 2 minus 1, which is n over 2, n plus 1 minus 2, which is n minus 1. Okay, so n into n minus 1 over 2, which is the correct result. And let's check. For a 3 cross 3 matrix, you should get only 3, what you have on the upper corner. Okay, so you put 3, n equal to 3. So you get 3 by 2 into 3 minus 1 is 2, 3. So it's correct. Okay, that's fine. Now I want to define what is a positive definite matrix. Maybe I should go to the next page. Okay. So I'll write down a Hermitian matrix. You know, Hermitian matrix is, if you take the dagger of it, you get it back. So H dagger is H. And daggering involves doing a complex conjugation and the transpose, both. So here is a definition. Shall I use a color? No. Let's see. Color. Okay. So positive definite matrix. And I will also look at positive semi-definite matrix. So anyway, let me define positive definite matrix first. Go back to black. So the definition is here. A Hermitian matrix H is positive definite okay, if for any non-zero complex column vector that you take, okay, and if you sandwich on the left hand side, on the right hand side of H these column vectors, you should get a positive quantity. So let me be more precise here. If for any non-zero complex column vector Z, vector Z, H star, so H star is the complex conjugate of Z, sorry, not H, Z star is the complex conjugate of Z, H Z. If you calculate this, okay, so here is a matrix H, you on the right hand side you put a column matrix, on the left hand side you have put a row matrix after taking the conjugate, and I'm saying that no matter what Z you take, okay, for all Z, if this quantity turns out to be positive, then I will say that H is a positive definite matrix. So let me read. A Hermitian matrix H is positive definite if for any non-zero complex column vector Z, H star Hz is positive. Okay, that's the definition of it. Another definition, I will use some color here. Okay, and the definition is a Hermitian matrix H is positive semi-definite. So I put semi here. If for any non-zero complex column vector Z, H star H is positive or 0. Okay, so the thing which I have written in green applies for only semi-definite. So if you always get positive, not 0, then it's positive definite. If you can also get 0, then it is called positive semi-definite. So that's the definition of it. We'll talk a little bit about this in a while. But before that, I will say something about a symmetric matrix. So you know, a symmetric matrices are the brothers of or cousins of Hermitian matrices. So what is a Hermitian matrix in the complex world is a real matrix in a real world. Okay, world of real vectors. So symmetric matrix is positive definite if it gives you a positive result for whatever Z you take. Okay, so you put a Z. Let's say the symmetric matrix is what I am calling S. Okay, and you multiply by any column which is a real column on the right hand side, and with the same column written as a row on the left hand side. And if you get a positive value for it, then it's a positive definite matrix. So let me write it down here. Real symmetric matrix is positive definite if for any non-zero real column, okay, let's call that column as A, you get A transpose S A as positive. Okay, if this is true, then your matrix S is positive definite. If, as before, you get 0 also, so let's say you can get 0 for certain vectors, then you call it as positive semi-definite or 0. Let me put it in brackets. Okay, so these are the definitions. Now first, let me give you a simple example. I think that will be a nicer thing to do. Yeah. First, let me give you a trivial example. So I am now looking at some the trivialist symmetric matrix is the identity matrix, and this is positive definite. Okay, because if you take any non-zero vector, let's say x1, x2, and so forth, xn, and you have identity matrix here, and you have this column x1 to xn, what you get is x1 square plus x2 square, so and so forth, xn square. Now no matter what x you take, okay, if x1 is minus 5, x2 is minus 20, some of them are 0 and some of them are positive, no matter what, because the squares are involved here, whatever you get is always positive. Okay, the only way you can get a 0 here is only if you take the vector itself to be 0. If all these x's are 0, then you get. But then we are saying the definition involves only non-zero vectors. Okay, so this is clearly a positive definite matrix. Let me give you a non-trivial example. Please pay attention to the positive definite matrices, because we are going to utilize this later when we talk about small oscillations. Okay, so let's see here. So I take the matrix to be 1, minus 1, minus 1, and 1. Okay, let's see now what we get. So what you do is, let's sandwich x, y, or you could have written x1, x2, doesn't matter. 1, minus 1, minus 1, 1, and xy. Okay, so I'm taking any x, any y. And what do you get here? You get here is x minus y square. So can you tell me what kind of matrix this is? Is it a positive definite matrix? Is it positive semi-definite matrix, or none of those? See, not every matrix will be a positive definite or positive semi-definite. They may be neither of these. So what do you think is the case here? So clearly, no matter what x and y you choose, you are going to get you are going to never get something which is negative, right, because of the square here. But you can get a 0, because if x and y are same, you get a 0. So if you choose 1, 1 for the vector, you get a 0. You choose 2.5, 2.5, you get a 0. Okay, but if you choose x and y to be different, you get non-zero. So this is clearly an example of a positive semi-definite matrix. Okay, that's good. Now you may ask, what happens if I take a real symmetric matrix, which is let's say positive definite or positive semi-definite, and I sandwich between two, I put from the left a z star and from the right a z, and where z is a complex vector. What happens to that? Okay, do I get something complex? Do I get something real? Okay, can I say something about it being positive definite or not in the complex space? And that's what I want to show you now. And the algebra is again quite simple. So let's say I take a complex vector z, column vector, column vector, and let's say I am given a positive definite matrix. Forget positive definite, let's say a symmetric matrix S. Okay, we will not specify any property of S. So I just take S, which is just symmetric. I'm not assuming any other property right now. And let's look at the quantity Z star S Z and ask what this is. Okay, so first thing I do is I take the Z and write it in terms of real quantities. So let's say the column Z can be written as this, where alpha and beta are real. Okay, and of course alpha is a column and beta is also a column, real column vector, and this is also a real column vector. So Z star would be your alpha minus I beta, and let's now construct Z star as Z. So you have an alpha plus I beta, okay, times your S times your alpha. Sorry, there was a minus sign here. I put a minus sign here. Alpha plus I beta. Okay. Now if you want to, I want to write this out in components. Okay, so I say, what am I using? K. So let me put a index K here, M here, and M. I'm also using Einstein Summation convention. Okay, so there's a sum over K and M, and this is how you write a product. Okay. Okay, that's good. So I have 4 terms here. So I multiply alpha S alpha, so I get alpha K S K M and alpha M. Let me multiply the betas. You get I square is -1, and there's minus already there, so that makes a plus. So you have a beta K S K M beta M. That's good. Then you have the cross terms involving alphas and betas. So let's look at them. You get alpha K S K M beta M, and there's a I sign, I here, and this one will give you minus I beta K S K M, and from here you get an alpha M. Okay, let's look at these 2 terms. You see, these K and M are repeated, they are dummy, so I can interchange. So instead of K, I can start writing M, and instead of M, I start writing K. So I look at this term. This one I will write it as, I keep the minus I also with me, minus I beta M S M K alpha K. Okay, so I've just interchanged the dummy indices, so which I am allowed to. Now your S is a symmetric matrix, so SMK is same as SKM as you saw earlier. So I can write this as minus I beta M S Km alpha K, which is nothing but minus I. Let me write down first alpha K SKM beta M. This term is same as this term except for the minus sign. Okay, so these 2 cancel. So this cancels against this, and what I'm left with is only these 2. And where alpha and beta are real vectors. So now you see, and first thing you realize is that even though your Z is complex, you can always split this into terms involving only the real parts, and there is no complex left around. Okay, and also if S is positive definite, then this will be positive and this will be also positive. Both these will be positive, which means this will also be positive even in the complex space. Okay, so that's one thing which I wanted to tell about, which we will utilize later when we talk about oscillations. Okay, and I want to talk about 2 very simple theorems which will again be very useful. Let's talk about them. So I call them 2 simple theorems because they are simple. What happened? Two simple theorems. Okay. Theorem number 1. Maybe some color will be nice. Okay. Okay, let me see what I've written. Okay, so let me write down. So the thing which I want to tell you here is the following. Let's say you are given some matrix. Let's call it phi. Okay, and I want to multiply some constant in each column of the matrix. So you look at the matrix phi as a collection of columns. So column number 1, column number 2, column number 3, and so forth. And each column I want to multiply some number. So in the first column, let's say I want to multiply 2. In the second column, I want to multiply 3. In third column, I want to multiply 25. Okay, like this. So what should I do to get this? And similarly, given a matrix phi, I want to multiply certain numbers in each row. Okay, so first row I want to multiply something, second row something, and so forth. So that is what I am looking at. Let me write it down. Multiplying each column of a square and cross n matrix okay, phi by a constant, and because these constants could be different, let me write down this by constants, okay, can be achieved by multiplying your phi from right hand side on right hand side, not from, on right hands, on its right side, on its right side by a diagonal matrix lambda. And what is that lambda? Lambda contains all the numbers which you want to multiply. So lambda is diagonal matrix with entries lambda 1, lambda 2, and so forth, lambda n. Okay, these are the lambda 1, lambda 2, these are the things which you want to multiply in each column. And what's the result? So here I am writing multiplying each column of a square and cross and matrix phi by constants can be achieved by multiplying phi on its right side by a diagonal matrix lambda, where lambda is this. And how do you achieve it? By multiplying on the right hand side, which is your phi. If you do this, okay, if you do this, then you will achieve what you have desired. Let me give a quick proof. It's trivial. So what I want to do is I want to start from let me use small phi to denote the entries. So let's say I have phi I k. Okay, k is the one which labels the columns. Okay, so what I want to do is go from here to phi I k, but each entry each column gets multiplied by some k. So lambda k, right? K, remember, k labels the columns, so that's why I'm multiplying by lambda k. That's good, that's what I want to achieve. And what is this? This right hand side I can write as, so there is no summation over k here, okay, no summation over k, even though the k is repeated. That should be clear. Now I can write this phi I k as phi I L delta KL, or let me write LK. It's symmetric anyway, so I can write delta LK, and you already have a lambda k sitting with you. Okay, that lambda k is there. So phi IL delta LK makes phi IK. There is a summation over L which is there, but not over k. Let me make it explicit by putting summation over L. Okay, so you agree with this? Now this I define as some matrix capital lambda and L K. Remember, there's no summation over k, so that's why I'm able to put this two indices. See, this has two free indices, L and K, and that's why I can create this matrix capital lambda with two free indices L and K. Okay, so that is correct. And what is phi I L times lambda L K? This is just the rule for matrix multiplication, right? So I am summing over L. So this I write as phi times lambda, and we are here looking at I kth element. Okay, so that's good. If you want to multiply each column, that is what you should do. So create a matrix lambda which is diagonal, and put all the numbers which you want to multiply on the diagonal entries. And if you construct this quantity, that's what is going to give you what you desire. Okay, theorem number 2 should be obvious now. Multiplying each row of a square matrix phi n cross n by, again I put different in brackets, constants can be achieved by multiplying phi from the left, by multiplying phi on left with, again, the same diagonal matrix which we had earlier, matrix lambda, which is diagonal of, whose diagonal entries are the constants which you want to multiply. Okay, that's what it is. So phi should go to lambda phi. That's what it is. Let me prove it again. It's simple, trivial as before. So you have here this thing. So take the phi ik element. Now I labels the row. So because you want to multiply in each row something, so on ith row you want to multiply lambda I. So this is what you want to achieve, right? This is where you want to arrive at. And this you can write as before as phi. Again, there is no summation over I, that you remember, even though they are repeated. So let me write phi lk delta il. Okay, if I write this, I have made this into phi ik. Okay, so that is how I have lifted off I from the phi and put on the delta. This you can always do. Okay, so given one index, you can always pull out from some quantity and put on another using a delta function. That's fine, but our lambda I is still there. There is no summation over I, but there is a summation over L. Let me make it explicit by putting this. That's good. Now again, as before, I define this as matrix lambda, and I is a free index, and L is also free, at least in here, in this part. Okay, and you see now what you have is summation over L, lambda IL phi LK, which is nothing but the matrix multiplication rule, lambda times phi, and you are looking at the I kth element of it. Okay, so we see that we have achieved it. Okay, I'll stop here, and we will talk more about matrices and other related quantities, which we are going to utilize in the later parts of the course. Okay, so see you in the next video.